Okay, welcome everybody. Today we have Alessandra Buonanno, who's a professor and director at the Max Planck Institute in Potsdam, if I'm not mistaken, and also professor in the Department of Physics at the University of Maryland. And she's a recipient of numerous prizes and awards. She's been working on the field of gravitational waves and LIGO for many years. And today she will talk to us about gravitational wave astronomy, advances and theoretical challenges. Professor Buonanno, thank you so much for being today with us. And please go on with your talk.
Okay, good afternoon. So I want to thank you first of all for the invitation, and I want to share my screen so that I can share the presentation. Very good. Okay, so let me go to full mode. Okay, so indeed, as I said, thank you very much for inviting me to give this colloquium. So I want to start with this picture that I'm sure many of you have already seen. It summarizes the observation of LIGO, Virgo, and Cagra during the last 10 years. On the y-axis is the mass of the black hole or neutron star, and going from the left to the right over time, the various detections, starting from the very first event discovered just 10 years ago, 150914. We use these numbers to represent the year, the month, and the day. In blue, you see here the black holes. The way of understanding this plot is that you have a black hole, another black hole, they merge with each other and they form a new black hole here. In 2017, there was the first observation of a binary neutron star, the 17th of August 2017. And also, I want to highlight the very large binary black hole, the largest detected so far. Here I made a mistake, this should be 23, the 23 of November 2023. We will see during the presentation some highlights on the other events. So in this talk, I would like to explain what is the theoretical framework that has underpinned the gravitational wave observations, what is the role that waveform models have been playing in detecting the signals and also extracting information. I will provide some highlights on astrophysics, fundamental physics, and test of general relativity with this observation so far. And then I will address, or at least I will point out that there are theoretical challenges that should be addressed in the future. And this is important in order to avoid incorrect scientific conclusions with runs that are becoming more and more sensitive, and also with future detectors, both on the ground and in space. So let me start with just one slide reminding that gravitational waves are a signature of dynamical spacetime that were predicted by Albert Einstein in two papers, the first in 1916. Here I have just the first page, where Einstein linearized the so-called Einstein equations, which I wrote here in full glory. R mu nu is the curvature of the spacetime, which depends on the metric g mu nu and its derivative in a nonlinear way. And on the right-hand side here, you have the energy momentum tensor of the source. So Einstein writes the metric like Minkowski or flat space-time metric plus a perturbation, very small. And then in a particular gauge, he can write the perturbation, satisfy this equation here, where the box is just the D'Alembert operator. So this resembles what we have in electromagnetism, where in the case of electromagnetism, T mu nu will be J mu, and H bar mu nu will be the field A mu. So actually, in the first paper, Einstein makes a few mistakes. in extracting the physical degrees of freedom, but this is corrected in a paper of 1918, where importantly he derives the so-called quadruple formula for the energy flux of gravitational waves, which is written here, although with a small error, a factor 2 that was then corrected by Eddington. And this formula just says that the flux depends on derivatives of the quadruple moment of the source. And so as possible gravitational wave sources, one can think of rotating dumbbell, like, for example, a binary star system. Now, of course, at the time, Einstein was not predicting gravitational wave from binary star system. They were not known. And also Einstein was very skeptical about we would ever detect these waves because they are extremely weak. So a few words now about the strengths of the gravitational wave from binaries. So I just told you that the gravitational wave depend on the derivative of the quadrupole. So if you take a binary system with two masses, M1 and M2, and you introduce the reduced mass and also the symmetric mass ratio, which is just the reduced mass divided by the total mass of the system, this quantity ranges between 0 when one body is much smaller than the other and 1/4 when the two bodies are equal to each other. Now, dropping any indices, because of course H, the strain, it's a tensor, being gravitational waves of spin 2 objects. So I drop here the indices, the strain is dimensionless, and what Einstein derived in the second paper, correctly, is that H depends on the second derivative of the quadrupole. D is the distance to the source, and here G is the Newton constant, and C the speed of light. Now, if you take a quadruple system, like the quadruple of a binary, then you can derive that h is proportional to the velocity square divided by the speed of light. For a circular orbit, you can trade the velocity to the orbital frequency just using the Kepler law. Inversely proportional to the distance, and then is proportional also to this parameter nu. Now, of course, the strain is weaker as the binary is very far from us. So ideally, one would like to have binaries in the solar system, but unfortunately, it's very unlikely that we see two binaries very close to merger, which is the range of frequencies where the detector can observe this system today. And that's why we have to go to much larger distances, encompasses many galaxies, cluster of galaxies, etc., to to have a probability. Like today, we are observing one binary black hole every 3 days. So you have to have many cluster of galaxies, and then in one of them you will have actually two black holes, so neutron stars being close enough to each other to be very close to merger to observe them. Now, if you put the binary in the Virgo cluster, which is the closest cluster to us that contains 3,000 galaxies, you can derive that H is very small, 10 to the minus 21. If you compute the luminosity or power, the energy per unit time, by taking this derivative of H and then squaring it, as you would do again in electromagnetism. In electromagnetism, of course, you have the dipole, not the quadrupole. You obtain a leading order in an expansion of B over C, this formula that tells you that V, in order to obtain a luminosity which is not negligible, has to be quite close to the speed of light because the power here is 10. C to the 5 divided by G is actually an energy per second, which is very large. It's actually similar or larger than the one of the all visible universe, and it's emitted only at in the last part when the two bodies are close to merger. Now, once the waves are emitted by the binary, they travel in the universe until they arrive to the Earth, and they are almost unaffected by whatever they encounter because gravity is very weak, although we will see later that there are effects like gravitational lensing, for example, that we have to take into account, especially as we start having many detections and better sensitivity. So we have interferometers to detect gravitational waves. The key idea behind the interferometers is that You have to see how the gravitational wave basically interact with free-falling bodies. The free-falling bodies, although they are hung by wires, are the mirrors at the end of the Fabry-Perot cavities, 4 kilometers long. And when a gravitational wave like impinges in the plane here, it stretches and squeezes the proper distance between the mirrors and creates a phase shift in the light. And so when the light recombines at the beam splitter, something actually leaks out to the photodetector. And in order to measure h of the order of 10 to the minus 21, we have to monitor the differential mode of motion in the mirrors at the level of 10 to the minus 16 centimeter, which is quite actually amazing. So now I'm interested here on gravitational wave from binary systems. And here we have the luxury that we can actually predict the signal in advance by solving the Einstein equations, as we will see later. And so the best method to actually pull out the waveform from the noise, and by the way, this plot here shows the strain noise, the noise in dimension of square root of hertz as a function of frequency. You can see the bandwidth between 20 hertz and a few kilohertz. So we use much filtering or signal processing, and I have here an animation. In the lower panel, you have the noise in black and hopefully a signal. So we correlate the template, which is in pink, with the data. And this correlation is shown in the upper panel, maximize on the parameter of the binary. And if a signal is present in the data, you can see the correlation can have a peak, and if this peak goes above a certain threshold, which has been set depending on the false alarm rate in the detectors, etc., one can claim a detection. Now, in order to do that, we need a template bank, and template banks have 100,000 of signals. Once the detection happens, we follow up with inference analysis to extract the properties of the source. And for that, we use millions of waveform models. So one has to basically generate very quickly these models, and they have to be very efficient. And we will see how this is done. So now let me go back to what I was saying a few slides ago. I was mainly focusing on the amplitude of the gravitational wave, but now I'm interested also in the phase, because in much filtering, what actually counts is actually the phase. You want to have a template that matches very well the signal, in particular the phase, otherwise you have a drop in the signal to noise ratio. So how this phase is computed? So first of all, notice that there is a factor 2 here. This comes from the quadrupole. If you had a dipole emission, you would have actually 1 instead of 2. So we use the energy balance equation. So on one side, we have the energy of the binding energy of the system, which you can compute as an expansion in V over C. At leading order, using just the viral theorem that allows us to express the kinetic energy in terms of the potential energy, you have the leading order term here. Then you need the luminosity, the flux at infinity, and this is just the formula now with all the coefficients, right, that I was just discussing with you before, and the one that actually was derived by Einstein, although not for binary systems. And then what you say is that, okay, there is an energy balance. The variation in time of the binding energy of the system has to be equal to minus the flux at infinity. And for quasi-circular orbit, as I was telling you before, you can express the velocity in terms of the frequency. And so now you can use this formula to derive d over d omega over dt. So you can rewrite in this form. And then you take an integration, actually twice, you integrate, and you get the phase, which actually enter this formula here. So this is, of course, not the way in which we compute the phase for the sophisticated waveform that include also merger and ring down, but it makes the point that what you need to compute is basically the binding energy or the conservative part of the dynamics and then the dissipation. Altogether, you have to get basically the dynamics correctly to compute then the phase, and then you compute the waveform on top of that. So I have here an animation to show you some of the events that were discovered by LIGO and Virgo. This corresponds to some events of the third run. And I want to make a point that for binary black holes, which are the first 5 events here, the signal is not very long, while for the binary neutron star, the signal is very long, as you can see here. Now, the gravitational wave frequency is a multiple of, because of the quadrupole, of twice the orbital frequency. The orbital frequency at leading order can be related to the separation between the two bodies, so the frequency is increasing over time because the system is losing energy because of the emission of gravitational waves. And at some point, the two bodies just merge, plunge and merge. And there is a frequency that you can compute as a rule of thumb. This frequency at merge, or the beginning of the plunge, is actually 4,400 Hz divided by the total mass of the binary in unit of the mass of the sun. So a neutron star has a mass between 1 and 2 solar masses, so it merges in the kilohertz. And because the bandwidth of the detector starts around 20 Hz, the signal is very long, as you can see here. But black holes have larger masses, up to, we are seeing 100 solar masses, and so they merge much earlier in the bandwidth, and that's why their signal actually are shorter. So if you increase the mass of the black hole, you go to million solar mass black holes, the signal is going to merge in the millihertz. And this cannot be seen on the Earth. We have to go to space, as we will see later. Now, a few words about the fact that the waveform bring information, or in the waveform there are imprints of the sources, the properties of the source that has emitted them. And I want just to show you this just with some waveforms. So from the frequency evolution, because the frequency increases over time, we infer the masses of the two binaries. If we know the amplitude of the wave and the masses, we can infer the distance from the Earth. If we know the time of arrivals, the amplitude and the phase at the different detectors on the ground, the two LIGO detectors, but also Virgo, and when operating Kagra, we can infer the sky location. Now, this signal here is for two bodies going on a quasi-circular orbit, non-spinning. If the black holes or the neutron stars have spin, and the spin are precessing around the direction perpendicular to the orbital plane, you can have modulations, which are also there if you have the two bodies moving not on a quasi-circular orbit, but eccentric. Also, you can compare the data to waveform in general relativity, which is what we do. But of course, you can also build waveform from alternative theory of general relativity, or include the deviation from general relativity in the waveform, and then test, is the theory of gravity general relativity or something else. Okay, so in order to then provide these waveforms for match filtering, to detect the signal, Bayesian analysis, to follow up and extract the parameter, we have actually to really work out, solve this problem analytically and numerically. So I want to make here an analogy. In Newtonian gravity, we are very lucky. There is an analytic solution that describes the orbit of the planets around the sun. You can also draw the ellipse numerically. In general relativity, this is not possible because general relativity is a nonlinear theory. You cannot actually have an analytical representation of the orbit at all orders. In fact, the orbit in general relativity is not even fixed in space, but it rotates like a rosette, as you can see in this very nice picture here that represents actually the star S2 going around Sagittarius star at the center of our galaxy. And also this ellipse shrinks over time because of the emission of gravitational waves. Nevertheless, one can look for approximate solution by solving perturbatively the Einstein equation, as we will see in a moment. So at the end of the day, we need people who do calculation with paper and pencil perturbatively, and we need people that solve the two-body problem in general relativity on supercomputers. Now, the reason why we cannot just use supercomputers is because it's very time-consuming to produce a numerical relativity simulation of two black holes going around each other, even for just 15-20 orbits, can take between a month or of the order of 6-8 months, depending on the mass ratio in the binary, the magnitude of the spin of the black holes. So here I have just a visualization of a simulation, equal mass non-spinning. The main part of the visualization here represents the flux of radiation which is emitted. In the bottom you see the two polarization, H plus and H cross, or the gravitational wave, and the colors, as you go toward yellow, the power is increasing until reaching this very large amount, 10 to the 23 times the luminosity of the sun in electromagnetic radiation, which is just emitted at the very end, as I was telling you before. Okay, so we have to solve this problem, which is called solving the two-body problem in general relativity. And I was just mentioning the fact that on one side we have numerical relativity. So this cube here is just representing the parameter space of the binary. So we have the mass ratio going from equal mass to asymmetric binaries. This axis here is the separation between the two objects. And going in this direction, you have the eccentricity, going from scattering of the two objects and the bound orbits. So numerical relativity covers a part of the parameter space. You cannot go everywhere because of computational, because it's very time consuming. So analytically, you can do, there are several methods that have been developed over the years, starting from post-Newtonian theory, which started with papers by Drost, Lorentz, and Einstein, Infeld, Hoffman. So this is an expansion of the Einstein equations in powers of V over C or GM over RC square, where R is the separation between the two objects. So it's valid for large separation, but then it becomes less and less accurate as the two bodies approach each other, where the velocity becomes large. And so the approximation is not very good anymore. You can do an expansion of the Einstein equation in powers of G, the Newton constant. So this is actually an expansion of G over R. It's an expansion in the valid for large separation, but does not expand in the velocity. So it's supposed to be more accurate if you go to, for example, large eccentricities. And then you can do also an expansion of the Einstein equation, not in velocity, not in separation, but in just mass ratio. So this will be strong field, but you have to assume that one body in the binary is much smaller than the other, and it's called gravitational self-force. Then there are methods to put together all these approaches. One of them, which have been very much involved, is the effective one-body approach, which combines the different methods and has also a physical motivated ansatz to phenomenological one to describe the mergering down, using also black hole perturbation theory. And this approach is then, improved using information from numerical relativity, as we will see in a moment. This is built in time domain. The waveforms are built in time domain. Then you can do also something else. You can build a frequency domain waveform, which are called phenomenological. And the idea here is that you basically take a numerical relativity waveform and effective one-body waveform, you blend them together because the numerical relativity waveform is limited in time. And then you take a Fourier transform and you basically build a frequency domain closed form representation of that frequency domain, of that waveform in frequency domain. And just to give you an idea, if you actually write the strain in frequency domain, the amplitude and the derivative of the phase during the spiral, intermediate region, and mergering down, you can see that the waveform in frequency domain is quite smooth. And so you can do actually representation in frequency domain. They are very fast to produce, but because you make some assumption in order to use a closed form expression, they are typically less accurate when you start including effects like spin precession or eccentricity than the previous one I was discussing. Now, with the larger and larger catalogs of numerical relativity waveform, today we have the largest one, around 3,500 numerical relativity waveform. People have started also to interpolate directly the numerical relativity waveform, and this goes under the name of numerical relativity surrogate. Here I have a plot to show in brown one of these numerical relativity surrogates. For a highly precessing system, you see the modulation in the waveform due to the precession of the spins compare with an effective one-body numerical relativity waveform and also with the numerical relativity waveform itself that was used to actually build the surrogate. Now, the waveform that the LIGO-Vigo-Italia collaboration have used so far assume that the black holes or the neutron star are in vacuum. Because in the case, for example, of black holes, if they had any gas around, for this kind of stellar origin black holes, the gas is supposed to be basically gone at the time when the two objects just merge with each other. However, considering that we are seeing more and more events, looking, observing maybe subpopulation of them, and also looking at what will happen in the future with the new interferometers, people are starting to include effects that are due to the fact that the objects are not just in vacuum. For example, you could have a large black hole with a small black hole going around it in an accretion disk. The black holes could move in a certain medium, could be also dark matter, and in representing the inclusion of these environmental effects that could be described also by scalar field, people do a computation using also Feynman diagram, which means that you can introduce new operators like scalar operators, etc. This diagrammatic representation with new operators can also be used to describe waveform, to derive a waveform perturbatively in alternative theory of general relativity. So this has started to be actually done, especially in the last 8 years. Okay, so now I have just one slide to tell you. I was telling you about this waveform, but I want to say how they are actually combined, the analytical with the numerical, through a process that we call calibration. I make the example of the effective one body. So one start with a waveform which is not calibrated to numerical relativity. In the upper panel here, you see in red an effective one body waveform for an equal mass system, non-spinning. And as the two bodies approach each other toward merger, you see that there is an accumulated dephasing. This is due to the fact that the analytical, semi-analytical waveform is less accurate, of course, than the numerical relativity one. So then what we do is that we include parameters in the model that then we tune to numerical relativity until the two waveforms agree very well with each other. And we repeat this process for all the numerical relativity waveforms at our disposal. So for example, for the current run, in our group, we developed the new version of the SOBNR waveform. S here stands for spin. We use 441 numerical relativity waveform from the SXX collaboration, which provides actually very accurate waveform that we are also part actually of this collaboration in our institute. Here in this plot, I'm showing all the numerical relativity simulation represented as points. This is the mass ratio. This is a combination of the spin in the binary. Then the waveforms are used for match filtering. So I was telling you to build the template banks. This is just an example of the template bank which uses for low masses 75,000 templates for binary neutron star, where we don't have to care about the merger, but for binary black hole, neutron star black hole, where the merger is important, of the order of a few 100,000 templates are used. There are, as I mentioned at the beginning, other waveform model, the IMR phenomenological, another version of the effective one body, which is called TOB-RISA-MES, and then the NR surrogate. So let me now start describing some of the results. So I start with some highlights from the third run. The 14th of August 2019, a binary, we say, with the puzzling companions was discovered. Why is puzzling? Because the mass of the primary is clearly the mass of a black hole, because a neutron star mass has a mass between 1 and 2 solar masses. So this is 23 solar masses. But the secondary mass, well, it seems to be too high to be the mass of a neutron star, given the equation of state of neutron star that are known, and perhaps is too small to be the mass of a black hole formed from a collapse of a star. So this remains somewhat a puzzle, and it's not the only event that has this. There is also another event with the same peculiarity. But observe also that the mass ratio here is 10. And now the more asymmetry you have in the binary, due to the difference in masses, in spin, the more complex or richer is the radiation. So here it's a representation of the event, the visualization represent here the total radiation, and now decompose in harmonics. Now you can decompose the plus and cross polarization in harmonics. So this is the 2-2, the quadruple, the main radiation, the 3-3, the 4-4, and close to merger, the 5-5. Now, the inclusion of these higher harmonics was important, just to tell you why actually we have to include this actually effect. So if you were not including higher harmonics, for example, using the EOBNR or the phenomenological waveform, you would get posterior distribution for the secondary mass much broader than when including higher harmonics, and also P stand here for the precession of the spin. And for this event it was particularly important because we wanted to nail down the mass of the secondary with high accuracy, and we got something of the order of 10%. Let me go to another event discovering the third observed near run. This is a numerical relativity simulation that we did in our department of the event. It's a very short signal because the masses are quite large, 90 solar masses, almost 67 solar masses for the secondary. And this has posed some challenge in theoretical astrophysics because there is a phenomenon called pair instability supernova that would predict that there is a black hole high mass gap between 40, 60 up to 120 solar masses, that for which we should not see black holes in that range if they come from the collapse of stars. This is mainly due to the fact that for some stars with large mass, as they evolve over time, they burn, etc. At some point, the photons create pairs of E plus, E minus, converting E plus, E minus. And now normally is the radiation is the pressure of the photons that counterbalance the gravitational collapse. But if at some point the photons are converted in E plus, E minus, this pressure is basically gone, and the star goes to a very explosive phase that basically leads the star to completely explode, leaving no remnant, no black hole at the end. Now, how these black holes would have formed, in particular the primary here? Well, one possibility is that this black hole came from the merger of two other black holes, so it didn't form from the collapse of a star. Some people also speculated that maybe this black hole formed from primordial origin. So there have been actually, there is a possibility that large density fluctuations during the early universe could have actually could have collapsed and formed black hole. So this would have happened even before, the first stars formed, etc. So now let me go to the exceptional events of the current run, which is ongoing. The 29th of May 2023, an interesting binary was discovered. It's a neutron star black hole. This was actually the visualization that we did in our department with with Tim Dietrich and Markin. So here the peculiarity is that, one of the masses is a neutron star. The other one is clearly not a neutron star, but if it is a black hole, again, it's a black hole with a quite low mass, which sits in the so-called lower mass gap. We don't see black holes with this mass in our galaxy from X-ray binaries. So this is also raising some questions about this object. Now, if we put together in the plane of the masses, M1 and M2, the binary neutron star discovered, the neutron star black hole discovered by LIGO and Virgo and Kagra collaboration. So you can see that this was the binary with a positive companion here. This event here is represented by this ellipse here and elongated region, posterior distribution here. And 170817 is basically the binary neutron star with multi-messenger observations here. This event, we couldn't observe the tidal deformation of the neutron star induced by the companion, by the black hole, because the signal-to-noise ratio was not very large. But one peculiarity is that the spin of the black hole is anti-aligned, is in the opposite direction with respect to the direction of the orbital angular momentum of the system, which also, raise some question on how the system formed. Now, the largest binary black hole observed so far, which I mentioned in my first slide, was discovered the 23 of November 2023. The signal to noise ratio is interesting. It's not, it's quite large. It's almost 23. The signal was incredibly short because the masses were large. And here you see the signal in frequency time plot. Let's look, in fact, at the masses. 137, the median 103, the median of the secondary object. This is actually a simulation that we did. So these are the spins of the black holes. And what is also interesting of this event, in particular of the primary, that the spin is quite large, is 90% of the maximum value. So not only these are the largest black hole, but also fastly rotating. Now, the total mass of the system is around 238 solar masses. The final black hole mass is 225. So 13 solar masses were just emitted in gravitational waves as the two bodies just merge with each other. Quite a lot. Now, these are not the only large black holes that have been discovered. There were other candidates, but they were more sub-threshold events because they had a false alarm rate less than 1 over a year, which is actually what we generally use as our threshold for events, for what we consider gravitational wave signals. Now, I wanted to point out that this event, we are only looking again at the merger ring down, and this raises some challenge for gravitational waveform because in this plot here, I'm showing the Poisson distribution for the masses M1 and 2. Being a very short event, the numerical relativity surrogate are our best templates, and this is the Poisson distribution just using our surrogate. But when we add the other waveform model, SOBNR, and in particular the phenomenological one, the phenomenological push actually this posterior in a different region of the mass of the secondary. And this is true also for the spins, Chi1 and Chi2. Chi1 is well determined, as you can see here, these are the 90% region, but Chi2, when we consider only an R surrogate, it's the Poisson distribution and here, but when adding in particular the phenomenological frequency domain waveform, this is pushed basically non-constrained in Chi2. This also points out that more work needs to be done to make actually the waveform closer to each other in the strong field in the region where you have only the mergering down. But now let me actually discuss what has been really the highlight of the fourth run, which is still ongoing, which is 250114. This paper came out, two papers actually, just for the anniversary of the 10 years from the discovery of 150914 this September. This is the clearest gravitational wave signal that has been observed today. It has actually signal to noise ratio 76 instead of 23. And the reason is because detectors have become more sensitive. The binary has almost the same parameter as the one of 150914, including the distance, around 400 megaparsec. But because the detectors are much better today in sensitivity, you can see how much better you can see the signal, compare the noise here with the noise that basically is here. Now, the larger SNR has also allowed for this signal to do interesting tests of general relativity. The test that we can do with LIGO, Virgo, and Kaga are different from any other test because we are testing high velocity and strong field gravity. And I wanted to highlight here one of the tests which is really very interesting. When a black hole is perturbed, the black hole is like a bell. It rings the space-time with peculiar normal modes. They are called quasi-normal modes. And this is basically what happens to the black hole. So when a black hole forms after the merger, the black hole is perturbed. And so during this phase, it emits these quasi-normal modes. I have a little animation. Here there are two black holes. They have different masses, different spins. and the frequency and decay time of the quasi-normal mode is different. The frequency and decay time in general relativity only depends on the mass and the spin. And so if you can measure more than one quasi-normal mode, you can actually test whether the black hole is the black hole, the solution derived by Roy Kerr in 1964 in general relativity or something else. And this was done for this event because of the large signal-to-noise ratio. And for the first time, one could extract the fundamental tone or quasi-normal mode and the first overtone. I will actually and use that to actually test the consistency with Kerr. We'll tell you more in a moment. But I also want to highlight that there was a test that was done for this event, which confirmed the Hawking area theorem. So basically, one has computed the area of the two black holes from the masses and the spin of the black hole during the in-spiral, the two component black holes, and compared that area with the area of the final black hole formed after merger. And one has shown that the area basically has increased. But let me go back to the quasi-normal mode. So on one side, you can use damp sinusoid against the signal to determine the presence of the fundamental mode and the first overtone. And this is what I was just telling you before. You can do also something else, which is less agnostic, which is basically you use the entire waveform, including also the in-spiral and the merger, not just the ring down, and you parameterize the quasi-normal mode, frequency and decay time, like the GR value plus a deviation. Just to show you what does it mean, it means that if you change now the frequency, for example, of the quasi-normal mode by a certain amount, you can change the frequency during the ring down in the way shown here in this animation. If you change the decay time, you can actually vary the amplitude of the waveform after the merger in this way. Of course, you use combination of them. And the nice thing is that by using this analysis, we could set the best bounds on the fundamental mode, but also for the first time, we could constrain the 4-4 quasi-normal mode, 440 quasi-normal mode. This plot is called, is basically a summary, which is called a spectroscopy test. So this is the final spin of the black hole, the final mass of the black hole. These are Poisson distribution. If you use, if you actually measure the fundamental mode with the damp sinusoid analysis, when you add also the first overtone, and all this Poisson distribution encompass this curve in black, which is the prediction of the final mass and spin using the component masses and spin of the black holes. So the fact that all this Poisson distribution, including also the 440, encompass this is a test that basically general relativity is not violated and that these black holes are the black holes of Kerr. Now, here I want to show you the simulation of this event, the two black holes going around each other. Now this slows down, the two black holes merge with each other. And now at this point, the simulation is just representing the fact that you have, okay, the first tone, which is the fundamental mode, the second tone, which is the first overtone, and what is called here the third tone is the 440 quasi-normal mode, and then this quasi-normal mode just dumped, away and leave the black hole there. The black hole is still there somewhere, the remnant black hole. Okay, so this event was so interesting because of the large signal-to-noise ratio that other tests of general relativity could also be done. And I want to mention here a test which looks at the in-spiral part of the signal, which resembles the post-Newtonian parameterized test that people have done in the solar system. But of course, this is not, the same as with the waveforms, with the gravitational waves. So in frequency domain, you can write the amplitude and the phase. The phase of the gravitational wave you can expand in post-Newtonian theory in powers of V. And in red here is the GR prediction for the coefficient, and then you can add the deviation, okay? This is a completely agnostic way of adding possible deviation. And then what you do is that when you do the Bayesian analysis, you sample on the 15 parameter on which the binary waveform depends on, the masses, the spin, the distance to the source, the direction in the sky, etc. But then you also add these parameters one at a time. Then you look at the posterior distribution for these parameters, marginalizing on all the others, and if the posterior distribution encompasses 0, then general relativity has passed the test. So in fact, general relativity has passed all the tests for all the post-Newtonian parameters, and the result is this plot here. You can basically then turn this into a bound on the parameters here. So for the different post-Newtonian parameters, starting from the leading order one, this plot, this star here, represent the bound that 250114 has established with two pipelines, flexible theory independent and what is called Tiger. You can see that the bounds of this event for the different post-Newtonian parameters is better than the square here, which is basically the bound that you can obtain by taking all the events of the fourth catalog, which just came out in August. So dozens of events. So with one single event, one could do better than combining several events. And this is due to the large signal-to-noise ratio in this event. Now, just to say that here, these vertical results here represent the parameter that describe the dipole emission. If you have a binary, so if you have a theory which is not general relativity, but for example, a tensor scalar theory, the radiation, it's the leading order is not the quadrupole, but the dipole. But for this event, the bound was not very good. The best bound is actually for the binary neutron star, because the binary neutron star was very, very long. So let me now say that the conclusion here is that you can look at the paper, which is on the web. A suite of tests were done, and this event has allowed to set the most stringent bounds than combining dozens of events, as I said, of the LVK fourth gravitational wave transient catalog. Now, the last event I wanted to talk about, which just came out this week, maybe some of you have heard about, it's two events that were discovered 1 month after the other in 2024. The paper has just been published by UpJ Letters. And the peculiarity of these two events is the following. So the masses, 20 and 6 solar masses, and 8, 17, are very similar to each other. However, this event has a larger signal-to-noise ratio, around 36, and the spin of the primary is actually above the orbital plane, while in this case the spin is actually anti-aligned. But in both cases, the spin are quite large. In this case, between 69 and 87%. In this case, because the signal-to-noise ratio was not very large, you see a very large spread in the maximum value of the spin of the primary. Now, the reason why this is creating some interest is because how this binary black hole formed with these large spins, and in particular in this case even anti-align. And a possible explanation again is that these are not from direct collapse of black holes, but they are second generation black holes. Basically formed from a merger of two other black holes, as the one that I was mentioning before, that I was telling you. Okay, so now I wanted actually to point out that the frontier for gravitational wave modeling today is to go beyond this quasi-circular orbit limit that for which now we have quite accurate waveforms. And I have here a simulation to show you the flux of radiation, and here in the bottom the waveform for the case in which the two bodies move on an eccentric orbit, not quasi-circular. And you see the waveform is much more complicated. There are bursts of radiation. Each time the two black holes come closer, they pass close to the periastron basically point. And the presence of eccentricity is quite important, because if we can measure, as I was just telling you before with the most recent event, that the spins are precessing and there is eccentricity, These are smoking gun, information for nailing down the formation scenario of the binary black hole. And there have been many papers in the last years to build waveform with eccentricity. We have already examples with eccentricity and spin precession and also align spin. But the work that has to be done is to make them accurate enough to use them for analysis and avoid systematic effects. Now, let me skip this and I want to go to you can ask me a question about the results of eccentricity. Let me go to the last part of my talk and discuss the future. So LIGO, Virgo, and Kagra are now in the fourth run. What you see here is the progression in the what is called the range. This is the distance at which we can see a binary neutron star. So the fact that it's increasing over time means that the detectors are becoming more and more sensitive. Now this run ends in a few weeks, and then there will be a period of commissioning, and then a new run will start sometime before 2027. At least this is the official, results today. I mean the official schedule. And so far, and this 05 run, we reach a much higher distance for binary neutron star. Then we expect in late 2020, maybe early 2030, to have a detector LIGO India, and there will be also further upgrades using the same facilities, which are called A-Sharp and Virgo Next. Now, these detectors are still going to see, even with these upgrades, binary black hole, neutron star black hole, and binary neutron star in our local universe, so up to a redshift 1, 2. But we expect new facilities on the ground, like Einstein Telescope and Cosmic Explorer. And with this detector, the sensitivity is going to improve by 1 or 2 orders of magnitude, depending on the frequency range. In particular, you see that these detectors are going to be much more sensitive at low frequency. This means that by making the bandwidth larger at low frequency, you can actually observe larger black holes. Remember the rule of thumb, 4,400 hertz divided by the total mass of the system. So you can actually bring in band and observe now thousands of solar mass black holes, because today we cannot see them because they merge outside the bandwidth. And by making the detector more sensitive, we can observe objects at much larger distance. So at larger redshift, even at the time before the first stars formed. Now, the characterization of this binary black hole and neutron star will be really amazing, because we will see many of these events. Just selecting the one with a signal to noise ratio larger than 100, the number is overwhelming, of the order of 10,000 per year for binary black hole, 500 binary neutron star per year. The signals are also going to be more complicated, because now we have, for example, a 1,000 solar mass black hole with a 10 solar mass black hole, and these are the snapshot of the orbit, for example, at 1 Hertz and 10 Hertz. These systems are likely to be also highly eccentric, with the spins precessing also for the black hole. Now, another important information is that we will have a detector in space called the LISA. This is just an animation showing the triangular configuration of the interferometer going around the sun behind the Earth. And the launch is predicted for, at the moment, for 2035. And LISA will open a new bandwidth. I should say also, there is the Chinese Tianqin and the Taiji missions that might happen on the same time scale. And these detectors are going to open the millihertz band. So this is the noise spectral density of the detector. And here there are a plethora of signals. So there will be this extreme mass ratio in spirals, a small black hole going around a large black hole. These are the tracks of different harmonics, massive black holes of 1 million, 10 million solar masses, basically merging in band and looking at them for months, if not a year. white dwarf binaries in our galaxy. The signals are not going to be transient, like for ground-based detectors. They are going to be there basically for all the time of the mission, at least many of them. Some of them, of course, like the massive black holes, will last for, as I said, months or a year. And so that analysis is going to be even more complicated. Now, I wanted to make a point about the challenge in accuracy for the waveform models. So I want to make two scientific cases. Let's consider a binary like 190814, which I was describing before, large mass ratio 10, but highly precessing. And let's assume that this binary is at a distance at which we saw it, so that the signal to noise ratio for the next run is much larger. In A sharp will be this, for Cosmic Explorer Einstein telescope, more than 2000 in signal to noise ratio. So let's consider the science case of cosmology. So this means basically that a binary is a standard candle. From the binary, if you can localize the binary in the sky, you can get the Hubble-Lemaitre flow velocity. From the measurement of the signal and extracting the parameter, you can get the luminosity distance. So you get basically the Hubble-Lemaitre parameter, which describe the expansion rate of the universe, right? So we did a test in which we injected in the data one of the state-of-the-art waveforms and recover with the other state-of-the-art waveform. So the SUBNR was used as signal and as recovery a phenomenological one. And this represented the posterior distribution for the luminosity distance. This was the true value. Now, depending on the SNR, the distance, the posterior of the distance, it's away always from the true value for more than 90%. And even the localization in the sky, the galaxy where the signal was, is here. And this is the reconstructed posterior distribution for the localization in the sky. So basically, if we were using the waveform we have today, we will get the wrong Hubble-Lemaitre parameter, which certainly is not going to help the so-called tension, in cosmology that we have today. The other example I wanted to make is about LISA and the quasi-normal mode extraction. So also in this case, a numerical relativity waveform was injected in the signal with quite a large signal-to-noise ratio, 200 for LISA, and it was recovered with this parameterized waveform model that can extract the deviation from the quasi-normal mode in general relativity. And you can see that the injected value was here and the recovery is here. So because of mismodeling, because the waveforms are not very accurate with respect to numerical relativity, we would have a false deviation from GR. So we have to be careful. We have basically to improve the waveform. In fact, several studies have pointed out that we have to improve the waveform by 2 orders of magnitude, even more for binary with matter. We have to include all possible physical effects because the signal-to-noise ratio and the sensitivity will be so good that we are going to see all these effects, eccentricity, the effect of so-called memory, astrophysical environmental effects. So now, the waveform is going to have imprints due to the accretion disk, as I mentioned before, the presence of a third body, and we have also to care about the fact that the signal could be lensed. So I mentioned this somewhat at the beginning. So if the waveform is emitted, and as the waveform travel up to, for example, the Earth or where the LISA detector will be, and it encounters a lens, depending on the mass of the lens, the signal is going to be distorted. So here the unlensed signal is in black and the lensed one is actually in color. And this is very nice. We could extract information about the lens, but what I'm trying to say is that this effect needs to be included because otherwise you will have systematics. So how do we want to do that? Well, we have to push the perturbative calculation, post-Newtonian, post-Minkowskian, gravitational self force at higher order. We have to combine them in the effective one body and phenomenological approaches more effectively. We have to do better calibration to numerical relativity. And there have been a lot of work in the last few years in post-Minkowskian calculations. This is the expansion in G that I described before. There is a large group of people coming from high energy physics that is applying a method coming from effective field theory to basically the classical two-body problem in general relativity. There have been also recent results of post-Newtonian calculation, and the frontier is to go to 6 post-Minkowskian or 5 post-Newtonian. So the post-Newtonian intertwine the expansion in V and G, that's why it's diagonal here. The expansion in PM is just in G. So we are basically, we have some results at 5 PM, but this is not complete. And also the 4 PM is not complete, that's why it's dashed. But as I said, ideally we should go to complete the 5 PM and go to 6 PM. Now, the other frontier is to get right the waveform for these MRIs, the extreme mass ratio in spirals. Here we need the second gravitational set force results. The waveforms are very, very complicated for MRIs, but this is very important if we want to get this exquisite measurement of the space-time around the black holes with LISA. Okay, let me now conclude. So with the first runs of the LIGO-MIGO collaboration, the tip of the iceberg of the binary population was observed. The third run has unveiled a richer picture. We detect for the first time the neutron star black holes, but the fourth run has already had many exceptional events and is still ongoing. 247 signal candidates observed so far. There are several questions connected to some of the events I was describing, these objects that are in the low mass gap, are they black hole, neutron stars, or maybe some other, maybe not black hole form from the collapse of stars. There are several events that are in the high mass gap or have peculiar spins, maybe they come from second generation black holes. I want to highlight again the future. So this plot is showing the signal to noise ratio of GW150914 like signal over time. We are 04 has provided this event, with almost 80 in signal to noise ratio. But if the same event will be observed in the future, we will have actually thousands, hundreds and thousands in signal to noise ratio. The number of events with SNR larger of 10 will also improve over time. And for that, we need actually to have this leap of 100 in improvement in accuracy if we want to avoid misinterpreting future observations. So I want to thank my department. A lot of work I showed is based actually on work of many postdocs and students. And also let me thank the LIGO-MIGO collaboration, the LISA consortium, and the Einstein telescope collaboration. Thank you for your attention, and sorry to take a little bit more time.
Thank you very much, Professor Buonanno, for this wonderful talk. So before we go on to questions, I first want to apologize because I'm supposed to be the chair of the session, but my 3 p.m. meeting turned out to be longer than expected. And
no
so
problem.
Thank you, George. Thank you, George, for going through what turned out to be an immense CV in a couple of seconds to introduce our speaker. And yeah, so apologies for that.
No problem.
Yeah, so we'll go on to questions. So are there any questions from the audience? And if you have one, please raise your hand in the Zoom. Okay, so while the audience is thinking, I actually have one question. So
yeah, someone actually has raised their hand.
Oh, okay, yeah, okay. So
but
please go ahead and ask the question. Yes.
Hello. Hello. I'm from Athens, Greece. Thank you very much for your very informative talk. If I understood well from your first few transparencies, if you plot the frequency of mergings of of primary and secondary black holes versus neutron stars, which are the more frequent events? You have more with black holes than neutron stars, because I would expect more binary mergings with neutrons. Yes, that's the one, which is very impressive, actually.
Yeah.
What is if you plot the frequency of say neutron star versus black hole neutron stars versus black holes, which are the more frequent ones?
Yeah, okay. So the intrinsic merger rate is larger for neutron stars, but
okay.
the black holes have a larger mass, and the signal is proportional to the total mass of the system with a certain power. So the reason why we are seeing more black holes is because they are stronger sources. But as I said, the intrinsic merger rate is actually larger for binary neutron stars. Does it make sense?
Thank you. Yes, of course. It makes sense. Well, can I ask a second question, or
Yes,
I
sure.
don't want to monopolize?
Sure, yeah.
Thank you very much. Now it's a sort of a big picture question here. Well, we know that we have supermassive black holes in the center of galaxies. I wonder whether these merging events, of course, it's sort of, you consider them in the big picture of things as triggering somehow the generation of a nucleus in the center of galaxies, which of course by accretion of matter can become much bigger and bigger. So what is the role, the physics role of mergings in the formation of supermassive black holes in the center of galaxies?
Okay, so I
binary
think
merging.
yes, I think you are more now referring to LISA, right? So you are referring to these massive black holes so LISA will see, this example here. Maybe I can go in play, I think. So, so this is 10 to the 7 solar mass binary,
Yes.
and the track is just this one. So these are two black holes that are originally were at the center of galaxy, but
Yes.
as you know, at some point galaxy also merge with each other. And
Yes.
so in this process, the two black holes come close to each other, and then they get in a bound orbit, and then they would eventually merge. Now, what is exactly your question? So what can we learn from the observation
about
of
the origin of supermassive black holes in the center of galaxies?
Yes.
Yes.
Well, I think Lisa can shed light on this because because of the large mass, we can see these events. I don't have now the plot to show you as a function of the redshift at large redshift, 10, in redshift.
Yes.
So this means that, and you will characterize how many of these objects there are as a function of redshift. And I think this is important because, in fact, people are trying to understand, also with the results of James Webb Telescope, when this very large black hole formed. And there are different scenarios. Did they form from what people call the heavy seeds or the light seeds, which means, do they come from what was the original object that formed them?
Yes.
Was it a cloud of gas that then collapsed, forming these very large, black holes of 100 solar masses, or from 1,000 solar masses? So because one will be able to characterize extracting the masses of these events, looking how they are at different redshift, one can shed light on them. In particular, for these, masses. Now, if you are interested in even larger supermassive black hole, then you have to go to lower frequency than LISA even. So, for example, I didn't mention at all this, but the pulsar timing array is looking at now really supermassive black holes of 10 to the 9 solar masses. But that's another story. They are not looking at very large redshift. So I think LISA, it's really very important to provide some, unveil some information about the early universe in terms of massive black holes.
Black holes. Thank you very much. Thank you very much. Thank you.
Thank you. Are there any other questions? I have a quick question. So basically your waveform, measuring a gravitational wave on Earth would be reducing a four-dimensional phenomenon into a time trace, right? And you mentioned that you want to include many physical effects to accurately model this waveform. But in that reducing process, isn't there going to be some sort of degeneracy? So can like more than one physical effect produce the same distortion or similar distortion in the waveform? And in that case, how would you like discern or distinguish which physical effect is responsible for the distortion?
Yeah, indeed, this can be a problem. So I wanted to come back to this event here, which was very short. So if you want, the point you are making is that you have to have enough length in your waveform to be able to disentangle this effect. If your waveform is very short, like for example, I was telling you before, I had actually this figure here. So I was saying, if you see these modulations in the signal, you can understand whether you have the precession of the spin or if you have eccentricity. But of course, in order to see this modulation, you have to see the signal for a certain length. If you were seeing only the last part, you might not actually be able to disentangle that. So on one side, I think it might not be possible, if you have a very short signal, it might not be possible to disentangle them. That's why to build detectors that have larger bandwidth is important so that you can see this kind of effect. For example, the eccentricity, we notice that at least up to eccentricity 0.2, 0.3, even if the binary is eccentric during the in-spiral, when you go to merger, the merger is quasi-circular. So if you see only the merger, it's very difficult to understand whether the system was eccentric. So I don't think there is a way, if the signal is very short, to really extract parameters that are degenerate with each other. And so we hope actually to have as much as possible long signal, or maybe large signal to noise ratio can also help, of course. But it is a struggle if the signal is very short.
Okay, thank you. In the interest of time, we'll take one final question from the Susmita Jana. Please go ahead. Susmita Jana.
I think you are muted. Hello. Yes.
Yeah. We can hear you now. Yes.
Okay. Yeah. Hi. Thank you for giving a nice talk. So I have a question regarding gravitational wave memory. So if we think in terms of the next generation detectors, so is there any preferences that if we consider a gravitational wave of certain frequency range, let's say if we think of LISA, then the millihertz frequency band is more sensitive, and if we think of the ground-based detectors, then obviously they operate in higher frequency band. So do you have any idea of that, which detector is more likely to detect memory?
Yeah. So I wouldn't exclude, I wouldn't say that one detector exclude the other. These are very different efforts. So in space, we have not gone in space with gravitational waves so far. And so LISA has been adopted last year in January by the European Space Agency. There is also a participation by NASA. So this mission is going to happen. And the peculiarity of this mission is the fact that you will see sources that you cannot see on the ground.
Yes.
And so it's completely, complementary. I didn't have time to explain what are these red things here, but the red are, we call them verification binaries, are binaries made of not black holes, but cataclysmic stars, etc., white dwarf. We know them from electromagnetic emission. And so we know more or less the distance. And so we should be basically seeing these sources. This is guaranteed.
Yes.
Now, the other sources, of course, there is, because we have not seen them until now, there is always an uncertainty in the rates, how many of these events we are going to see. We expect that at least a few massive black holes, if not 100, will be seen by LISA, and similarly in the case of MRIs. Now, for the facility on the ground is another story. So the LIGO, Virgo, Cagra detectors are using the current facilities, and if one wants to continue on the ground to in particular see, for example, the stellar origin black holes, and the binary neutron star. The binary neutron star cannot be seen in space because they are in space. They would be not chirping. They will be just like single source monochromatic, but the signal to noise ratio is not very large. So if you want to study the equation of state of neutron stars, you have to be on the ground in the kilohertz, and you have to be, very sensitive. And this is, if you want to do multi-messenger astronomy with binary neutron stars or neutron star black holes, you can do it on the ground. And of course, the black holes, although we have seen already many, they are bringing new information. They will with new facilities, because we are going to see them basically covering the entire universe with those masses, because they are very sensitive, this detector. They will go up to very large redshift. And so I would say, so first, from a more funding situation, things are separate, because the detector in space are funded by space agencies and detector on the ground by other kind of agencies. So they are not fighting with each other. And also scientifically, they are really targeting very different signs.
Yes. So I was asking about the gravitational wave memory.
The gravitational wave
memory, yes. So
sorry, I didn't. I thought
I'm
for 5
sorry
minutes.
that maybe I was not very clear.
I didn't notice that you said memory. Okay, so for the memory, yes, the detectors at low frequency would be better, because the memory effect,
more time we have, I mean the period of the oscillation, then I think it's more probable to observe the memory.
Sorry, can you repeat a moment? I don't think
I'm saying that the time period of the gravitational wave.
So I think you are saying about the memory, the fact that if you include the memory, the waveform, instead of so let me take an example. So if you have memory, the gravitational wave signal, instead of after the ring down going to 0, it will go basically to a constant, right?
Yes.
So it is this transition to a constant that one wants to measure. And from what I remember, so people have written several papers with single event will be very difficult, but if you combine several events, you can actually measure the memory. You can also do it with Cosmic Explorer Einstein telescope, but I thought that the best bounds come from a detector like LISA, from what I remember.
Okay.
Because of the large also signal to noise ratio in the merger. Because LISA will see, 3,000, 4,000 signal to noise ratio just in the merger.
Yes. So that will improve a lot.
Yeah.
Hmm.
I saw a hand, but I don't know.
Oh, was there a
Yes.
hand up or?
Yes, it's me again. Can I ask a third question?
Sure,
Yeah.
sure. Yeah.
I mean, for me,
so-
we can discuss. I don't have to. I can stay. Yeah.
Okay. Well,
Just okay. Before you ask the question, people,
somebody else.
please feel free to leave. It is getting
yeah,
long,
for
but
other people,
but I
yes.
will. Yeah. But I will allow the question to be asked. Yeah.
Okay, just a question, a quick one. What is the holy grail of gravitational wave astronomy? Is it like to detect gravitons, for example, out of gravitational wave detection? I mean, what would it take in terms of technology to identify gravitons through gravitational wave detection? In terms of your quantum sensors or whatever. I mean, how far away you are from there?
Well, you know, this, so the gravitational waves are classical waves, right?
Sure.
So they contain, from that point of view, they have a very, very large number of gravitons. So there have been, I mean, I would say, not with the gravitational wave detectors, you are going to see the gravitons. Now, there have been some papers in the last year where people, but not with gravitational waves, you know, people are trying to look at experiments where you can measure the graviton, and there have been also some controversy, I mean, discussions. So, but with gravitational waves, I don't see how you can do that because the waves are really classical and they contain a very, very large number. N is very large, being N, you know, I mean, of gravitons. So I don't know if you had something specific in mind, but I don't see how you can.
No, I don't. I was just wondering, in terms of technology, what would it take, say, in 50 years in terms of in quantum sensoring, in sensing methods?
Yeah,
I don't know.
yeah, I don't know. I'm afraid I don't know. With gravitational waves, I don't know because I mean, the way in which the detector work, they are not measuring.
They're measuring. Okay. Thank you very much. We'll think about it. We'll think.
Okay, you can think about it.
Thank you.
Okay, so I think that should wrap up the colloquium. So let's all thank Professor Buonanno again.
Okay,
clap.
thank you for. Okay, bye. Bye. Have a nice evening. Bye for you. Bye.
Thank you so much. Thank you so much. This concludes the colloquium. Thank you all.